Okay, so my name is Prathaj, and my research question is Zone 2 cardio, is it all hype or the key to fighting cancer? So, a little bit of background on the problem I'm trying to solve is, Zone 2 cardio is all the rage these days. Um, if you're into health and fitness, you probably have heard of Zone 2 cardio. Um, but I wanted to see if this doing this type of cardio has any benefits other than making you faster at whatever you do. So like cycling, I like cycling. If you do a lot of zone two cardio, you're gonna get faster. Um, so the key idea is that when you do cardio in this zone, you build a lot of muscle, like slow twitch muscle fibers that have a lot of mitochondria with something called the MCT1 transporters. And what these MCT1 transporters do is they take lactate, which is a byproduct of glycolysis, and shove it back into the Krebs cycle to create more ATP. And this lactate clearing capacity is what we're gonna model with our cellular automata, because all cells use glycolysis, including cancer cells, to produce energy, and a byproduct of glycolysis is lactate, and cancer cells produce a lot of lactate. So what I wanted to model is, if these slow twitch muscle fibers with, a lot of these MCT1 transporters, if they would have like a non-local effect um, on cancer cells. So like, cancer cells produce a lot of lactate, but if you have like a lot of slow twitch muscle fibers, that you get from zone 2 cardio, like would their lactate clearance capacity would be enough to contain the spread of tumor cells in like other parts of the body? Um, so how do we model this? So I obviously use a cellular automata, uh, like a 2D grid, where each cell could have um, could could be one of three states. So it could be an athlete cell. These are the special cells with that have a lot of like MCT1 transporters. The normal cells, which are just regular cells that you don't exercise, and cancer cells that are just tumor cells. Um, so the way I set this up is I created two other grids, one for glucose levels and one for lactate levels. So every cell has a corresponding glucose level and a lactate level. And the differentiator between these cells is how much glucose they consume and how much lactate they produce. So for nutrient diffusion, um, to make it a little more realistic, I use this diffusion kernel. Uh, so basically, we're also assuming a steady supply of like glucose to this cluster of cells. So when glucose gets to the cell, like the way it's diffused is the cell gets 40% of the glucose to itself, shares 10% with its neighbors, with its top, bottom, left, right neighbors, and like 5% with like its diagonal neighbors. That's what we're doing for like the nutrient diffusion. Um, and then, once the glucose has been diffused, you know, different cells have like different consumption rates. So, like, cancer cells have a higher consumption rate, athlete cells have a higher consumption rate than normal cells, but all of them, they consume some amount of glucose. And then and after, uh, glucose has been consumed, there's also a phase where lactate is produced. Like all cells produce lactate, but cancer cells produce the most lactate. Those are also like hard coded. And after this phase, we have the cancer spread phase. So then we check the Moore neighborhood of every single cell to see if um, the lactate levels are above a certain threshold, and if there are any cancer cells in this Moore neighborhood of this cell. If there is a cancer cell and there's a lactate level above like a certain toxicity threshold, we assume the cancer is going to spread. So we turn this normal cell or like this athlete cell into a cancer cell. So I coded this up in Python, but thanks to WebAssembly, I was able to run it in the browser in my blog post. So what we're gonna do, like the parameter that I really wanted to tune is the athlete cell ratio, which is the amount of athlete cells you have because we're using like a 200 by 200 grid. Um, I wanted to see if the more you exercise, the more of these muscle slow twitch muscle fibers you get. So I wanted to just model like what ratio of these athlete cells would help you fight the growth of cancer. Um, because and you could say all those other factors like how much lactate um, a cancer cell produces, how much lactate your athlete cells can shovel back into the Krebs cycle. All of that is you can chalk it up to genetics a little bit to keep the model a little simple. So we'll start the simulation. Let's start with like 60% of athlete cells. So these guys over here are the athlete cells, and these guys over here are normal cells. So you could introduce a tumor anywhere you want in this application. So I'll just introduce a tumor over here. And as you can see, nothing is happening because this is an athlete cell. It consumes lactate really fast. But if I introduce a tumor, let's say over here, ooh, that is really fast. It spreads rapidly. So we can reset and try other percentages. So let's try 85% athlete ratio. So introducing a tumor in a normal cell, and it's not spreading. So these guys over here do have some non-local effect of containing the tumor that's not in the athlete cell region. But you can go ham and like keep introducing tumors. I mean, at one point I think they're starting. Yeah, this spreading slowly. This just started spreading. So yeah, this is what I wanted to demonstrate. Like if you have a high percentage, a high concentration of these athlete cells, um, they do have a non-local effect on containing the spread of like these tumor cells. You could have a tumor cell in your liver, but if you have a lot of like mitochondria or like these slow twitch muscle fibers in your legs, they will help you contain the spread of cancer. That's the idea. Of course, like this is a very simple, like extremely simple model. So here are some results. So this is a run for a ratio of 20% athlete cells, and I ran it like 5 times, and you can see anytime a cancer cell gets spawned in a normal tissue, it just spreads rapidly, except for that one time where this cancer cell spawned in a athlete tissue. So these are all like random spawn points for tumor cells, and then we'll look at like a similar run for 80% ratio, and you can see like in these two scenarios, the cancer stops spreading after a while, even though it's in a normal tissue. So one thing I would note that in when I created these simulations, the diffusion was a little different. Like because we have to simulate like how glucose is being replenished. So you assume like blood is constantly flowing to the tissue, and this was a lot simpler. I just like replenished a row in the grid with like ones, and that was my assumption of like, okay, this is how your glucose is being replenished. But in the simulation over here, it's a little more complicated. We're like making it's a little more realistic, like a network of like a blood. Like it's simulating a blood vessel basically. So that's why the cancer cells spread more rapidly. But the idea is the same. But over here, like you can see, like the cancer cells don't spread as much, and yeah, that is my presentation.